printing from prototyping all the way to mass production volumes. Markforged, if you haven't heard of us, is a bit of a unique 3D printing company. We print strong parts. We're the only company with a printing platform that includes printers, software, and material that creates parts from plastics to composites to metals. Let's take a look at the agenda for today. We'll start with an introduction about our company. Then we'll talk about product development cycles, what some of the differences are in product development between hardware and software. And then we'll focus in a little bit on metal in particular. And we'll talk about how metal printing can be scaled. Okay, about Markforged. We were founded out of MIT in 2013. These logos at the right are several of the companies that our employees have in their backgrounds. Scientists from Bell Laboratories, Twilio, Sonos, that's my background, Cisco, Merkai, and Enernoc. Our headquarters is in Boston, Massachusetts. We're up to 102 employees and growing fast. We shipped our first composite printer in 2014 and grew at 300% this year. We achieved profitability in Q1 of 2017. We've shipped thousands of printers to over 50 countries around the world. Markforged customers are global, but we offer local on-site support and training in every region. We've seen customer success across all verticals: aerospace, automotive and transportation, government, consumer, medical, footwear, and academics. Here at Markforged, we're all about empowering engineers. Our mission is to unlock the next 10x innovation in design and manufacturing to liberate designers and engineers from decades-old slow processes. Let's talk about some of those processes, but we'll start with using sort of a reference example, which is the software development cycle. 50 years ago, computing was all done on a mainframe. This is the DEC PDP-7, which was introduced in 1965, and it was the state of the art in computing, but it was all local. It was a big machine, and it was expensive, and it required a trained operator to run. Here's what computing looks like today. It's entirely different. Now all computation is in the cloud, running remotely and parallelized to expedite calculations. In software, time constraints to make a change or spin a new version are measured in seconds. This accelerated computing power has led to groundbreaking work in software over the last few years because anyone can access massive compute capacity at the touch of a button. So now your software development cycle looks typically like this. This is a mid-tier feature implemented by an efficient software team, but you can see that they'd spend a couple weeks on the design, a couple weeks on prototyping and implementation, a small test window, and then they can push it directly to the market. So your entire time from product concept to shipping is 1 to 2 months total. And when you ship, you can ship inherently at scale because it's very easy to replicate on the side of software. There is no limitation of ramp. So I talk about this to contrast it specifically with today's hardware development cycle. New software is pushed in days. In hardware, it can take years. This is why creating value in hardware is so slow. As an example, let's look at the automotive industry. You may have seen the news this morning that the Tesla Model 3 production is behind schedule. They only made 260 units last month against their 1,500 unit plan, falling short due to what they call bottlenecks in production. Let's talk about what those bottlenecks are. Cars are especially complicated, having hundreds to thousands of custom parts. Each part needs to be prototyped and manufactured and finalized, tooled, and then produced. And all those parts need to be assembled in the process that puts them into a car that fits together tightly, and they need to do that at high volume. But actually, each piece of that car, of which there's thousands, has to go through dozens of iterations and prototypes before reaching its final design. Every one of those iterations and prototypes needs to go through Frank. Frank is the machine shop operator. It needs to have the part be designed, drawn out, machined in-house or externally, brought in, tested, and then iterated on. So this is what you get. Even for small, simple products, the process takes years. 3D printing has traditionally helped accelerate prototyping on that first section there, but primarily for parts that do not require strength. Our composite printers have helped accelerate tooling design for the manufacturing lines. But when you compare hardware development to software development, the differences are obvious. Hardware development is a slow process, it's cumbersome, and it's about 10 times as long as doing software iterations. So we need to close this gap if we want hardware development to be as fast as software development. Why is there such a big difference? It's all about cycle times and physical things. It turns out we've been making parts pretty much the same way for thousands of years. This is a copper awl that was recovered from a grave in Israel. It's one of the earliest examples of a cast part. It carbon dates to between 5 and 7,000 BCE. This part was made in a mold. We still mold metal today. The process hasn't changed a lot. The molds are more complex, but we still pour metal into a shape to frame it into its final part. Elon has pointed out time and again that what really matters is being able to scale up production volume as quickly as possible. This is one big reason that manufacturing has such a long lead time and why many hardware companies experience delays. So how do we make hardware more like software? And why hasn't metal printing scaled? Well, metal printing hasn't scaled because of a few reasons: printer cost, part cost, reliability, and process speed. But today we're going to tell you about our vision for the future of metal manufacturing and how it scales effectively through 3D printing. But we'll start by talking about a technology that is already scaled into mass production, which we leverage heavily in our metal 3D printing technology, and that's called metal injection molding. Metal injection molding parts are used in mass production every day. Apple uses them on their Lightning connectors and their hinges for their MacBooks. And Pratt & Whitney used them in their Pure Power PW1500G engines. Metal injection molded components are being used in hip implants, in automotive all over the world, and they're done at production volumes in the millions. The way metal injection molding works is you take metal powder and you bound it in plastic, and then you injection mold the plastic just like you would a plastic part. Well, what we do is instead of injection molding that material, we print it. And so I'm going to tell you a little bit about the process we call atomic diffusion additive manufacturing, or ADAM. It starts with designing your part, printing it, putting it through a sintering process, and you're left with your final fully dense metal part. And much of the post-process after printing is exactly the same as metal injection molding. So we'll start with the design. You design your part in your CAD program like you normally would. When parts are sintered in the metal injection molding process, they shrink by about 20%. So we'll scale that part up automatically for you in our software. All you have to do is upload your STL. And then you hit print. In the case of this end effector that I just showed you for a robot arm, it takes about 3 hours. And we'll step through some of these slides showing the printing process happening. You see that the part is being created layer at a time, much like a traditional extrusion process that we do on our composites printers. Once the part's been printed, it's just like an injection molded part. It's in what we call the green state. And from here on out, it's metal injection molding post-processing. So there's 2 steps. The first is called the wash. You put it in a cleaning fluid, which removes half of that plastic binding that's binding the metal powder. In the case of this part, you have to wash it for around 9 hours. And it takes out the wax-based portion of the binding material. And then it goes into the furnace. This is the sintering step. You place the parts on a ceramic bed. The part is heated up to about 85% of its melting temperature, and it fuses to 98 to 99% dense metal. During this process, parts shrink by about 20%, and the sintering time takes about 16 hours. And there you go. You've got your final part. They come out of that process ready to be used. They have fully isotropic strength. And their dimensional accuracy is very similar to those cast parts we reviewed that were being poured into molds. You may post-process these parts using CNC machining or any other metal post-processing that you would traditionally use, just like you would for casting or metal injection molding. But the great part about this process is that it's designed for scalability, and it's using a scaling process that is already well understood. On the composites or plastics side, this extrusion process is used frequently to create large volumes of parts. In-house at Markforged, we print over 11,000 sample parts a month on a farm of 30 Markforged printers working in parallel, and we have 1 untrained operator running those machines. Our Metal X printer is 10 times lower cost than traditional powder bed-based printing processes that are on the market today. They often run $1 million, and ours starts at $99,000. It's much less expensive. And in the future, this technology has already been shown to fundamentally scale down in cost, so we'll watch it go down the cost curve and become more and more affordable. And then we leverage existing technology. So there's some prototyping furnaces you can get. The Sinter 1 and the Sinter 2 are offered by us. Those run forming gas, 4% hydrogen, at normal atmospheric pressures and have ceramic retorts. But when you're ready to step up and go to high volume mass production, there's already existing production scale metal injection molding post-processing equipment ready to go. So that's our view on the future, which is to take a printing process that is already shown to scale down in cost and to put them together in parallel, just like blade servers have done in software, so that you can have a high capacity to make parts, a low per instance cost, so you get speed, cost, and all of the parts that you make are exactly the same throughout the entire process. That's important. That means that the part that you get at a mass production scale is exactly the same as the prototype part that you tested and built to begin with. And so when you qualify a part, you don't have to redesign or requalify it for a scaled production. This is going to accelerate things dramatically because now we're going to get rid of the tool. We're going to get rid of the lead time on that tooling. You'll be working, validating your prototype parts. And as soon as it's validated, that's the same part you can use in mass production. And so there you go, from prototype to production. We start with a high volume process, metal injection molding, and we did something unique, which is scale it down to be prototyping. And then it scales right back up by putting metal printers in parallel, smart affordable hardware, which is then managed collectively through a cloud software platform. And here's what your new design timeline looks like. Now you still spend that time designing the part, the 4 to 8 weeks, but your prototyping, tooling, and low volume high production are all dramatically accelerated because now you're just printing these parts instead of doing the entire manufacturing process. And when you're ready to add more volume, you simply put more printers in parallel, and you've taken a 1 to 2 year process and cut it down to 4 to 6 months of time. So that's parallelization with Atom. You cut the product to market workflow by 75% by scaling manufacturing efficiently and allowing a great degree of freedom of complexity and design, which is all the benefits you get with 3D printing. All right, let's answer some of the questions that are coming in. We probably won't get to all of these, so if we don't answer your question, we'll follow up with an email. All right, let's see. Tolerance and shrink from sintering. Tell us a little bit more about that. That's a great question. So like I mentioned, when the parts go through the sintering process, they shrink by about 20%. The tolerances we see are size dependent. So you have parts that are a few thou accurate per inch. The larger the part, the less the accuracy. The best way to think about these parts is like a cast part, and they're near net shape. If you have a critical tolerance that you need to achieve, you can machine it just like you would post-machine a cast part. Do you have a cost analysis tool so that we can find out what the final price of a part will be? Absolutely. So I encourage you to go online to try out our Eiger software. You can find it at markforged.com. There's a software demo pop-out on the side. It'll ask you to put some information in because you'll have a unique account. Then you can upload any part you'd like. You can select any of our materials, including stainless steel, and it'll tell you how long it will take to print and what the cost of the material going into the part is. How can you connect multiple Metal X's in parallel? Great question. Our software is designed to work across a fleet of printers. Internally to Markforged, we have over 125 printers throughout our org, all running on the same software. You can select a build that you've designed to be printed and just print it across any number of printers sort of easily and quickly. And as that scales, you start to get a greater degree of flexibility over time in terms of the utility for that process. How do the physical properties of 3D printed material compare against cast metal? So our material testing is showing that our performance is very similar to cast performance. We'll be publishing some data on that later. What materials can you print? That's a good question. We can print any materials that can be metal injection molded because we print the binding material that holds the metal powder. Metal injection molding covers a wide range of metals. There's about 200. Our beta materials are steels. That's stainless steel, 174 316L. We have A2D2 and H13 tool steel. We'll do titaniums and Inconels. And then you'll see us move on to softer metals like aluminums and coppers. And then there's a last question is the sinter process connected to Eiger as well? And the answer is yes. Our software is connected to the washing station, the printer, and the sintering furnace. So we handle an end-to-end experience for you to make sure that the part you intend from the beginning goes correctly through the process and is the right part at the output. Okay, thank you very much for your time and joining the webinar. We look forward to having you as a guest on a future one, and that's the end.